Hello, in this lecture we will find the size of line segment AE. In the drawing we have square ABCD. We know that angle BED, this angle is a right angle, it equals to 90 degrees. We also know that line segment BE equals to 2 units, line segment DE equals to 8 units, and we want to find out the size of line segment AE. So I will connect together points A and E by straight line. Actually, we want to find out the size of the red line segment AE. Okay, so we will connect together points B and D by straight line. BD is also the diagonal of square ABCD, but BD is also the hypotenuse of triangle EBD, because triangle EBD is a right triangle because it has one angle BD equals to 90 degrees. So we can write down that triangle EBD is a right triangle Therefore, we can implement the Pythagoras theorem in the right triangle EBD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle EBD is DB. So DB square, that is the square of the hypotenuse, equals to the sum of the squares of the perpendiculars, equals to BE square plus ED square. Okay, so DB square equals to BE square, but BE equals to 2 units according to what is given us in the question. So BE square is 2 square, 2 square is 4, plus ED square, ED equals to 8 units according to what is given us in the question. So ED square is 8 square, 8 square is 64, and DB square, according to question number 1, equals to 64 plus 4 is 68. Here we take a root of question number 1 and we will get that dB equals to the square root of 68 units. So we actually found out that dB, the diagonal of square ABCD, equals to the square root of 68 units. And we also know that all the angles inside a square are right angles, they are equal to 90 degrees, therefore angle BAD, this angle will be equal to 90 degrees, and also angle BCD, this angle will be also equal to 90 degrees. In the next step, I will present to you rule number 1. According to rule number 1, the diagonals of a square bisect or cross is the same word. Bisect or cross it means they divide it to two halves. Bisect the angles of the square into 45 degrees angles. I will read rule number 1 again. Rule number 1 states that the diagonals of a square bisect the angles of the square into 45 degrees angles. So we actually know that all the angles inside the square are right angles, and according to rule number 1, the diagonals bisect the angles of a square, so it means that the diagonals creates angles of 45 degrees because they divides the angles that are all equal to 90 degrees to two equal angles. That is meant to mean that every angle that they create is equal to 45 degrees because 90 over 2 is 45 degrees. So according to rule number 1, we have diagonal BD of square ABCD, and according to rule number 1, this diagonal BD bisects angle ADC, that is to say this angle will be equal to 45 degrees, and this angle ADB will be also equal to 45 degrees. Likewise, angle, this is a right angle, so in the diagonal DB bisects this angle, it means that it divides this to two equal parts, that is to say this angle will be equal to 45 degrees, and this angle will be also equal to 45 degrees according to rule number 1. So actually, this triangle BCD, is the right triangle. Triangle BCD is the right triangle. So, in the right triangle BCD, cosinus 45 degrees equals to DC over DB. I'll repeat again. In the right triangle BCD, cosinus 45 degrees equals to DC over DB. We will define side DC of square ABCD as y, that is to say DC equals to y units in its size. So we will get that cosinus 45 degrees equals to DC equals to y, so we'll substitute DC by y over dB. We've already found out that dB equals to the square root of 68. So in total we got that cosinus 45 degrees equals to y over square root of 68. This will be equation number 2. But we know that cosinus 45 degrees equals to square root of 2 over 2, and it equals to y over square root of 68. Here we will multiply equation number 2 by square root of 68. And we will get that square root of 2 over 2 times square root of 68 equals to y. We know that 68 is 34 times 2, so we'll substitute 68 inside the root by 34 times 2. We will get that y equals to the square root of 2 over 2. And we substitute 68 by 34 times 2. Actually, we have a rule that states that the square root of a times b equals to the square root of a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2, so I will write it down. and this is multiplied by square root of 2 over 2, it equals to y. So here we have square root of 2 times square root of 2 is 2, so I will write it down. Over square root of 34 over 2 equals to y. 2 over 2 is 1, so 2 will get cancelled. And we actually found out that y equals to the square root of 34 units. Y is one side of square ABCD, and we know that all the sides of a square are equal to each other, therefore all the other sides will be also equal to the square root of 34. So we write here that y equals to the square root of 34. BC will be also equal to the square root of 34 units. AB will be also equal to the square root of 34 units. And finally AD will be also equal to the square root of 34 units. In the next step I will present to you rule number 2, and we will implement rule number 2 in our drawing. Okay. Rule number 2 states that if a line segment AB subtends two equal angles, on the same side, then the square ABCD, the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So I will read rule number 2 again. Rule number 2 states that if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have line segment AB so this is actually line segment AB, and we know that two equal angles rest on line segment AB. So the first angle that rests on line segment AB is this angle, angle ACB rests on line segment AB, and it equals to theta. And we also have another angle that also equals to theta, that also rests on line segment AB. This angle ADB, also equals to theta, and it is also rests on the same line segment AB. Then, according to rule number 2, the quadrilateral ABCD this quadrilateral ABCD is inscribed by a circle. So quadrilateral ABCD is inscribed by a circle. As you can see from the drawing, quadrilateral ABCD is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. Okay, that is actually the explanation of rule number 2. Okay, so if we have line segment AB and two equal angles that they are both rest on line segment AB, then the quadrilateral ABCD, this quadrilateral is inscribed by the red circle, and the 4 points A, B, C, and D lie on this red circle. That is the explanation of rule number 2. And we can actually implement rule number 2 in our drawing. We will implement rule number 2 in our drawing, because in our drawing we have angle EBD that equals to 90 degrees, subtend or rest on line segment DB. I'll repeat again, angle BED, this angle that equals to 90 degrees, it is a right angle, it subtends on line segment BD, and this angle BAD, it is also equals to 90 degrees, and it is also subtend on the same line segment BD. So therefore, according to rule number 2, the quadrilateral AEBD is inscribed by a circle. Quadrilateral AEBD is inscribed by a circle. The quadrilateral in the green color, quadrilateral AEBD is inscribed by a circle. Quadrilateral AEBD in the green color is inscribed by a circle, and the 4 points A, E, B, and D lie on that circle. So we will actually draw this green quadrilateral AEBD inside this circle. I repeat again, this quadrilateral AEBD is inscribed by this blue circle. So I will paint it in the green color exactly as I did in this quadrilateral. It is the same quadrilateral that I copied here. This is actually the green quadrilateral from the original drawing. This quadrilateral is inscribed by this blue circle according to rule number 2. I will explain again rule number 2 in this drawing. Angle BAD equals to 90 degrees. And angle BED also equals to 90 degrees. This quadrilateral is exactly a copy of this quadrilateral. They are exactly the same. And as you can see in this drawing, we have those two right angles rest on the same line segment BD. I will repeat again. Those two right angles, angle BED is a right angle, and angle BAD is also a right angle, and they are both subtend or rest on the same line segment BD. Therefore, according to rule number 2, the green quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, that is actually the implementation of rule number 2 in our drawing. Okay, this drawing is the implementation of rule number 2. We actually implemented rule number 2 in this original drawing, and after the implementation of rule number 2 in this original drawing, we got this drawing. So this is the implementation of rule number 2 in our original drawing. Okay, so right now we have quadrilateral AEBD, the green quadrilateral, that is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, so we arrived to this drawing by implementation of rule number 2 in our original drawing, in this drawing. Okay, so in the next step I will present to you rule number 3, and we will implement rule number 3 in this drawing. So rule number 3 states that rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So I will read rule number 3 again. Rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that first of all we have a quadrilateral that is described by a circle. Okay, so we have quadrilateral ABCD that is inscribed by this circle, or this circle blocks quadrilateral ABCD. So inside this circle we have quadrilateral ABCD, or quadrilateral ABCD is inscribed by this blue circle. So as you can see in this drawing, we have quadrilateral ABCD in the red color that is inscribed by this blue circle. We also know that side AB of quadrilateral ABCD equals to A units in its size, side BC of quadrilateral ABCD equals to B units in its size, side CD of quadrilateral ABCD equals to C units in its size, and side AD of quadrilateral ABCD equals to D units in its size. And quadrilateral ABCD has two diagonals. Diagonal BD equals to X units in its size, and diagonal AC, the second diagonal of quadrilateral ABCD, equals to Y units in its size. So rule number 3 relates to quadrilaterals that are inscribed by a circle, like in this drawing. It is not related to other quadrilaterals, but only to quadrilaterals that are inscribed by a circle, like in this drawing. And according to rule number 3, whenever we have a quadrilateral that is inscribed by a circle, like in this drawing, then the product of quadrilateral ABCD diagonals, that is actually X times Y, equals to the sum of the products of its opposite sides. As you already know, any quadrilateral has two pairs of opposite sides. Side AD is opposite to side BC, that is the first pair of opposite sides, and side AB is opposite to side CD, that is the second pair of opposite sides of quadrilateral ABCD. So the first product of the opposite sides, it is actually B times D, and the second product of quadrilateral ABCD opposite sides is A times C, and the sum of products of its opposite sides is B times D plus A times C, or the first product plus the second product, it is actually BD plus AC, and that sum of the product of its opposite sides equals to the product of its diagonals, that is to say X times Y. Again, X times Y, that is the product of its diagonals, equals to the sum of the squares of its opposite sides, that is actually BD plus AC. Okay, so that is the explanation of rule number 3. So whenever you have quadrilateral that is inscribed by a circle, you can implement this rule number 3. It states that the product of the quadrilateral diagonals, in this case is x times y, equals to the sum of the products of its opposite sides. That is actually BD, it is the first product, plus AC, it is the second product. So BD plus AC, it is the sum of the product of its opposite sides, and it equals to the product of its diagonals, that is to say x times y. So actually that is the explanation of rule number 3. And now we will implement rule number 3 in our drawing. So here we have quadrilateral AEBD in the green color is inscribed by the blue circle. Whenever you have quadrilateral that is inscribed by a circle, you can implement rule number 3. So we have here quadrilateral that is inscribed by a circle, therefore we can implement rule number 3 in our drawing. And according to rule number 3, the product of quadrilateral AEBD diagonals, it is actually AB times DE. And that product equals to the sum of the products of its opposite sides. Again, quadrilateral AEBD has two pairs of opposite sides. Side AE is opposite to side DB, and the product of those two opposite sides is AE times DB. That is the first product of the opposite sides. And the second product of the opposite sides, we know that AD is opposite to side EB, and the product of those two opposite sides is AD times EB. And the sum of the product of the opposite sides is product 1 plus product 2. In other words, the sum of the products of the opposite sides is AE times DB plus AD times EB. And that sum of the product of the opposite sides equals to the product of its diagonals, that is to say AB times DE. Okay? So equation number 3 is the implementation of rule number 3 in our drawing. Okay, I will repeat again. The product of quadrilateral AEBD diagonals is AB times DE, and that product equals to the sum of the product of its opposite sides. It equals to the sum of the products of its opposite sides, that is to say the first product is AE times DB, and the second product is AD times EB, and the sum of the product of its opposite sides is product 1 plus product 2. Okay, this expression is the sum of the product of its opposite sides, and it equals to the product of its diagonals, that is to say it equals to AB times DE. Okay, so I will copy again equation number 3, and we will put the data inside this equation in order to find out the value of AE, or the size of line segment AE that we are looking for. Okay, so we have, I will copy again equation number 3. Equation number 3 states that AB times DE equals to AE times DB plus AD times EB. So I copied again equation number 3. This is a question number 3. And now we will put the data inside this equation. So what is AB? From this formula, we can see that AB equals to the square root of 34. And what is DE? DE equals to 8 units according to what is given us in the question. So we actually found out that AB equals to the square root of 34 and DE equals to 8 units, and all equals to AE is the missing line segment, so we will leave it as it is. What is DB? DB equals to the square root of 68 units. I will repeat again. We left AE as it is. DB equals to the square root of 68 units. And what is AD? AD equals to the square root of 34 units. And EB equals to 2 units according to what is given us in the question. So we actually found out that AD equals to the square root of 34 units and EB equals to 2 units according to what is given us in the question. So here we have square root of 68, but we know that 68 is 34 times 2, so we'll substitute 68 by 34 times 2, and we will leave the other variables as they are without any change. We will copy the other variables as they are. So it is actually square root of 34 times 8 equals to AE, and we will substitute 68 by 34 times 2, plus square root of 34 times 2, according to the rule that square root of A times B equals to the square root of A times square root of B. The square root of 34 times 2 will be equal to the square root of 34 times square root of 2. And we will copy the other variables as they are without any change, plus square root of 34 times 2, here is multiplied by AE, line segment AE, and it equals to the square root of 34 times 8. This is equation number 3. So here we will divide equation number 3 by square root of 34, so square root of 34 will get cancelled here, here and here. And what is left after we cancelled square root of 34? What is left, it is actually 8 equals to square root of 2 times AE plus 2. So here we will subtract 2 from equation number 3, and we will get that 8 minus 2 is 6, equals to square root of 2 times AE. We will divide equation number 3 by square root of 2, and we will get that AE, line segment AE that we are looking for, equals to 6 over square root of 2. Okay? We know that 6 equals to 3 times 2, so we'll substitute 6 by 3 times 2, and we will get that AE equals to 6 is 3 times 2 over square root of 2 So here we will multiply this expression by square root of 2, and then we will divide it by square root of 2, so we change nothing. Therefore it is allowable to do this operation. AE equals to 3 times 2 over square root of 2. We will multiply it by square root of 2, and then we will divide it by square root of 2. Here we have square root of 2 times square root of 2 in the denominator. Square root of 2 times square root of 2 is 2. So we write it down. AE will be equal to 3 times 2 times square root of 2, and square root of 2 times square root of 2 is 2. So 2 over 2 is 1, so 2 will get cancelled. And we actually found out that the size of line segment AE it is actually equals to 3 times square root of 2 units, or in terms of numbers, line segment AE equals to 4.243 units. Okay, I will repeat again. The size of this line segment in the red color, line segment AE, equals to either 3 times square root of 2 units, or if we want to represent this expression in terms of numbers, it equals to 4.243 units. So this line segment AE equals to either 3 times square root of 2 units, or in terms of numbers, line segment AE equals to 4.243 units. Okay, and that is the answer to the question. Now I'll summarize the lecture. Actually, we wanted to find out the value or the size of line segment AE. We have, in the drawing, we have a square ABCD. We know that line segment EB equals to 2 units, line segment DE equals to 8 units, and we want to find out the value of AE, or the size of line segment AE. This line is the red color, and the first thing that we did is we joined together points B and D by a straight line. So the red line BD is the straight line that we draw, and actually DB is also the diagonal of square ABCD, but it is also the hypotenuse of triangle EBD. Triangle EBD is a right angle because of the fact that this angle is a right angle. So because of the fact that triangle EBD is a right angle, we can implement the Pythagoras theorem in the right triangle, triangle EBD. And according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is dB square, and it will be equal to EB square plus DE square. Again, I repeat again, in the right triangle, triangle DEB, the square of the hypotenuse is dB square, and it equals to the sum of the squares of the perpendiculars. That is to say, it equals to BE square plus ED square. So dB square equals to EB square. We know that EB equals to 2 units. It is given as the question. So BE square is 2 square is 4. Plus DE square. DE equals to 8 units according to what is given us in the question. So DE square is 8 square is 64. 4 plus 64 is 68. So we found out that dB square equals to 68. We took a root out of equation number 1, and we found that dB equals to the square root of 68 units. Okay? So here, the diagonal of square ABCD equals to 68, square root of 68 units. Then I presented to you rule number 1. Rule number 1 states that the diagonals of a square bisect. Of course, it is the same word. It means they divide it to 2 equal parts. So the diagonals of a square bisects the angles of a square, the angles of the square, into 45 degrees angles. So we actually know that all the angles inside the square are right angles, and according to rule number 1, the diagonals, in this case we are talking about diagonal DB of square ABCD, this diagonal bisects the angles, that is to say, divide it to 2 equal sizes. So if the size of any angle inside the square is 90 degrees, and it divides it to 2 equal angles, it means that it divides the angle to 45 degrees and 45 degrees. So this angle will be equal to angle CDB will be equal to 45 degrees, and the second part of this angle will be also equal to 45 degrees. Likewise, in this side, diagonal DB bisects this angle that is a right angle. So this first part will be equal to 45 degrees, and the second part will be also equal to 45 degrees according to rule number 1. So this angle is a right angle, therefore triangle BCD is a right triangle. And in the right triangle, triangle BCD, we know that cosinus 45 degrees equals to DC over DB. In the right triangle, triangle BCD, cosinus 45 degrees equals to DC over DB. We define DC as y, that is to say the size of DC is y units. Therefore, cosinus 45 degrees, that equals to DC over DB. So DC equals to y, so we substitute the DC by y, and we already found out that dB equals to the square root of 68. So in total, cosinus 45 degrees equals to y over square root of 68. We also know that cosinus 45 degrees equals to square root of 2 over 2. So in total we got that square root of 2 over 2 equals to y over square root of 68. Here we multiply the equation number 2 by square root of 68, and we got that y equals to the square root of 2 over 2 times square root of 68. We know that 68 is 34 times 2, so we substituted 68 inside this root by 34 times 2. And we got that y equals to the square root of 2 over 2 times square root of 34 times 2. And we have the rule that square root of a times b equals to square root a times square root of b. So according to this rule, the square root of 34 times 2 will be equal to the square root of 34 times square root of 2. Okay, and in total we got that y equals to the square root of 2 over 2 times square root of 34 times square root of 2. Square root of 2 times square root of 2 is 2. So we got that y equals to 2 times square root of 34 over 2. 2 over 2 is 1, so 2 will get cancelled, and we found out that y equals to the square root of 34 units. So one side of square ABCD equals to the square root of 34 units, and we know that all the sides of a square are equal to each other. So if this equals to square root of 34 units, then all the other sides will be also equal to square root of 34 units. Okay? Then I presented to you rule number 2. According to rule number 2, if a line segment AB subtends two equal angles on the same side, then the quadrilateral ABCD is inscribed by a circle, and the 4 points A, B, C, and D lie on that circle. So what is the meaning of rule number 2? The meaning of rule number 2 is that if we have line segment AB and we have two equal angles that rest on line segment AB, angle ACB equals to theta, and it rests on line segment AB, and angle ADB also equals to theta, and it also rests on the same line segment AB. Therefore, according to rule number 2, the quadrilateral ABCD, this quadrilateral is inscribed by this red circle, and the 4 points A, B, C, and D lie on this red circle. Okay, and we actually can implement rule number 2 in our drawing. Why? Because in our drawing we have those two right angles, and they both subtend on the same segment line BD, DB or BD. Angle BED, this angle is a right angle, and it subtends or rests on line segment BD. Angle PAD, this angle, it is also a right angle, and it is also subtend on the same line segment BD. Therefore, because of the fact that we have two equal angles that subtend on the same line segment BD, therefore, according to rule number 2, the quadrilateral AEBD in the green color is inscribed by a circle, and the 4 points A, E, B, and D lie on this circle. So this is the implementation of rule number 2 in our drawing. I'll repeat again on rule number 2. Angle BED is a right angle, it equals to 90 degrees, and it rests on line segment BD. Angle BAD, this angle, it is also a right angle, and it also rests on the same line segment BD. Therefore, according to rule number 2, the green quadrilateral AEBD is inscribed by this blue circle, and the 4 points A, E, B, and D lie on this blue circle. Okay, this drawing, it is actually the implementation of rule number 2 in our original drawing. After we implemented rule number 2 in our original drawing, in this drawing we got this drawing. Okay, then I presented to you rule number 3. Rule number 3 states that if quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. I will read rule number 3 again. If quadrilateral ABCD is inscribed by a circle, then the product of its diagonals equals to the sum of the products of its opposite sides. So what is the meaning of rule number 3? The meaning of rule number 3 is that if you have a quadrangle ABCD, this in the red color, that is inscribed by this blue circle. So whenever you have a quadrangle that is inscribed by a circle, you can implement rule number 3. And we have here quadrangle that is inscribed by a circle, therefore we can implement rule number 3. And according to rule number 3, the product of quadrangle ABCD diagonals, it is actually x times y, and that product equals to the sum of the products of its opposite sides. Quadrangle ABCD has two opposite sides, two pairs of opposite sides. The first pair of opposite sides is AD is opposite to BC, and the second pair of opposite sides is AB is opposite to side CD. And the first product of the opposite sides, we know that AD is opposite to side BC, and the product of those two opposite sides is B times D, or B times D. This is the first product of the opposite sides, and the second product of the opposite sides is A times C. And the sum of the product of the opposite sides is product 1 plus product 2. That is to say, it equals to BD plus AC. So the product of the opposite sides, that is BD plus AC, equals to the product of its diagonals, that is to say, it equals to x times y. I repeat again, the product of its diagonals, that is x times y, equals to the sum of the products of its opposite sides, this is actually BD plus AC. So actually this is the explanation of rule number 3. Then we implemented rule number 3 in our drawing. So this is our drawing. This is the drawing that we got after we implemented rule number 2 in the original drawing, in this original drawing. So we have here quadrangle AEBD that is described by the blue circle. Therefore we can implement rule number 3 in this drawing. Why? Whenever we have quadrangle that is described by a circle, we can implement rule number 3. So according to rule number 3, the product of quadrangle AEBD diagonals is AB times DE, AB times DE, and that product equals to the sum of the products of its opposite sides. The first product of its opposite sides is AE times DB, AE times DB. The second product of the opposite sides is AD times EB. And the sum of the product of its opposite sides is product 1 plus product 2. That is to say, it equals to AE times DB plus AD times EB. And that sum of the product of the opposite sides equals to the product of its diagonals, that is to say, equals to AB times DE. Okay, so I repeat again, the product of its diagonals, that is AB times DE, equals to the sum of the products of its opposite sides, that is actually AE times DB plus AD times EB. Okay? Again, equation number 3 is the implementation of rule number 3 in our drawing. And the only thing that is left now is to put the data inside equation number 3. I copied again equation number 3 here in this page. This is equation number 3. We know that AB equals to the square root of 34 units. DE equals to 8 units. It is given us the equation. AE is the missing line segment, so we leave it as it is. BD equals to the square root of 68. AD equals to the square root of 34 units, and BE equals to 2 units. It is given us the equation. So here we substituted 68 by 34 times 2, because 34 times 2 equals to 68. And we change nothing except this change, we change nothing, so we copied equation number 3 here. And so here we have square root of 34 times 2 equals to the square root of 34 times square root of 2 according to the rule that the square root of a times b equals to the square root of a times square root of b. Okay, and this is the only change that we did from here to here. And so here we divided the equation number 3 by square root of 34. So square root of 34 will get cancelled. And after we cancel square root of 34, what is left is actually this equality, that 8 equals to the square root of 2 times AE plus 2. We subtracted 2 from equation number 3 and we got that 8 minus 2 is 6, so 6 equals to the square root of 2 times AE. We divided equation number 3 by square root of 2 and we got that AE equals to 6 over square root of 2. But we know that 6 is 3 times 2, so we substituted 6 by 3 times 2. And we got this equation number 3, that A equals to 3 times 2 over square root of 2. Here we multiplied this expression by square root of 2 and then we divided it by square root of 2, so we changed nothing. We got this expression. Square root of 2 times square root of 2 is 2. So in the denominator we will have 2. And 2 over 2 is 1, so 2 will get cancelled. And we found out that AE equals to either 3 times square root of 2 units, or in terms of numbers, the size of line segment AE is 4.243 units. I will repeat again. The size of this line segment AE in the red color, it equals to either 3 times square root of 2 units, or in terms of numbers, the size of line segment AE equals to 4.243 units. Okay, it equals to 4.243 units, or we can also express it as AE equals to 3 times square root of 2 units. Okay, that is the answer to the question. Thank you very much.